What we're now going to try and do is build up our distance ladder, this idea of how do we measure through all the different lengths of the universe. So before we do that, I got to establish why. Why can't we just use parallax and keep going beyond and beyond? Well, the smallest parallax angles that astronomers can directly measure. This number has a little bit of tweaks into it as technology has grown. We've gotten very impressive techniques with satellites, but for now, just say for a nominal value, the smallest we can get is a parallax angle of 0.001 arc seconds. Well, 0.001 arc seconds, how far away is that in distance? Well, d equals 1 over parallax angle. So 1 over 0.001 arc seconds multiplied by our correct units, 1 parsec times 1 arc second. Cancel the arc seconds. That's 1 divided by 1 parsec divided by 0.001. Plug in your calculator or do the powers of 10 in your head. And you'll find this is 1,000 parsecs or 3,260 light years. Well, nice. But the universe at large that we see is pushing 90 billion light years. So, at best, our parallax measurements can get our neighborhood, our local neighborhood. We're going to have to do a lot more impressive techniques to get the rest of the universe. We're going to need new tools. And quick disclaimer, when I say the observable universe, this is a scientifically accepted term. We're talking about not just what we can see from here at Earth. We're talking about the physical limit of light in the universe. There's a lot built into that sentence there, and we'll save discussions for that in future sections. All right. The universe is big. Look at something like this, the Sagittarius star cloud. On average, the distance between all these stars is pushing 25,000 light years. Parallax just isn't going to cut it to get all these different distances. Look how dense the universe is and how big it is. So, this is where we've come up with the idea of the cosmic distance ladder. And here's a picture summarizing the scale of the problem. Parallax, or at least our old school techniques of parallax. This is about the range, right? Here's the Milky Way. Here's our solar system in a ring or a rung of the Milky Way, one of the arms. And parallax could do the nearby stars. We've gotten better. Parallax has gotten better. So we've managed to start getting to the outer edges, maybe start getting towards the center of the Milky Way. This is what the extent of parallax can do for us. And then keep going. There's going to be crossover in our different techniques as we start measuring out towards other galaxies or the biggest, furthest distances away from us. So as we build up these new tools, we're going to use this in our ladder analogy. Each new technique is a rung of the ladder. And the rungs are going to have a little bit of overlap. So I'll be able to use one rung to compare with the one below and the one above. I mean below or above how far away objects are. So my parallax is going to have crossover with these other techniques. And then so on and so forth. And we're going to use this as tools to calibrate and just check ourselves. We want to make multiple measurements and make sure they all agree. So, for the purpose of this course, this is going to be our cosmic distance ladder, right? We're going to have Earth, and we're just going to build up using radar, then parallax, then our main sequence fitting, Cepheid variables, and supernovas to start measuring the different distances in the universe. One thing I'll emphasize here, this scale, this plot here, is not linear. We keep shifting orders of 10. So each subsequent step is orders of magnitude bigger than the previous step. So some of these techniques will have a wide range. The Cepheid variables cover a wide range, even though the blue region in this graph looks short. This is akin to a logarithmic scale. All right, so let's go through these techniques one by one. talk about their benefits, what they're used for. And we'll start off with radar. That's our closest, right? And the powerful thing about radar, yes, it's only really good for our solar system. Light follows an inverse squared law, which you're going to hear me reference over and over again, that inverse squared law. And the ability of our radio waves to be powerful enough to go out there and come back, and us have it be measurable, just diminishes the further and further away we try to measure with radar. But if you're in the solar system and we can aim a radar system at you, we're going to get all sorts of awesome data about you. We're going to be able to resolve spatially what the object looks like. Depending on what the surface material is, the radar might be able to penetrate a little bit, get through the surface layers, and we'll actually use that radar information to pull out the composition, the interior composition of that thing. So we use this radar to map out asteroids, comets, dwarf planets, satellites. Satellites, I mean moons. And the planets. We're using radar to get not only highly accurate distance measurements to those objects, but figure out what they're composed of. So radar astronomy is one of the most prevalent types of astronomy out there because you get to have massive amounts of information on the local stuff. Parallax, I'm not going to repeat myself. Go watch part 1 again. But I will add to this is that we have greatly improved the limits of parallax. The Hubble Space Telescope, and soon its successor, the James Webb Telescope. There are going to be better and better improvements on this. They still use techniques of parallax. Hubble can do about 10,000 light years away from us. 10,000 light years away. So parallax is getting better and better. But that's still not good enough to get outside of our galaxy. And we know the universe is vast and filled with billions of galaxies. So let's try another technique. And I absolutely love this one. This is called main sequence fitting. And we've made calls to this. We've referenced this technique before in other section videos. But let's go through this in detail. What you're going to do is you're going to look at a star cluster. Powerful thing about star clusters, the grouping, the cluster of stars, they're close together, which means that they roughly formed around the same time. And if they're all in the main sequence, we'll be able to plot them and figure out their spectral types. So what you do is you look at the clusters, right? Count as many stars as you can in that star cluster, and you put them on the main sequence. All right? Those clusters, what's going to happen is that we're going to look at the age of these stars, how luminous they are. And since we know they're on the main sequence, the star clusters should follow a main sequence, but they'll be shifted. They'll be shifted from the expected main sequence. Why shifted? Well, because of their increased distance. Remember, we're not directly measuring the luminosity. We're measuring the magnitude, the brightness, how bright these objects are. So we're effectively measuring the main sequence scaled, shifted by how far away the stars are. Since these stars are all in a cluster together, their distance is all effectively the same. For astronomical purposes, they're the same thing because of just how far away they are from us versus each other. So we've created a basically second line in the HR diagram in the star cluster. And we say, look, we can figure out what spectral types each star should be. Well, figure out what shifts need to be done so that if they had followed the main sequence, if they are up here correctly, how far away do they need to be to shift that brightness down? Because remember, brightness decreases with distance. The further away an object is, the dimmer it's going to appear. So, as a recap, you identify a star cluster, make an HR plot of all the stars you can in that cluster. You're going to find a main sequence, but it's going to be shifted down from what you expect because of the distance. And since you know the main sequence lines, you can figure out what the spectral type of the stars are, and then calculate how far that star needs to be for its luminosity, its brightness, to be diminished. Its brightness to be diminished because of how far away it is. Absolutely love this technique, everyone. This is phenomenal science. So let's keep going. We're going to keep going further and further out now. Our next technique, right, are Cepheid variables. So remember, the Cepheid variables, these are stars that are pulsating. There's helium in their atmosphere that's globbing onto electrons to cool off a little bit, then re-emitting them. So these Cepheid variables are stars that are going to pulsate. They are pulsating, getting bigger, smaller, and their luminosity goes up, down, and fairly periodic. Here's one over a couple of days, couple of weeks. Right? We'll have periods that can last somewhere between days to years is the time span, most of them falling in the weeks to months range of the brightness going up and down. And the important trick, if we can find the time of these oscillations, how long it takes to go from trough to trough or peak to peak, it doesn't matter. You measure the period. For this particular case here is about 9 days, 9-day period. You measure the period, how long it takes, and that, through physics and astronomy calculations, corresponds to luminosity. Well, I've got the luminosity. I know how bright it is. You just measure how bright it is. So with the luminosity, you get the distance to that star. Right. This picture here, this diagram here, it's a drawing. It's representing little us. There's our sun in the Milky Way galaxy. And here's a bunch of Cepheid variables near the galactic center, just outside the horizon of what our parallax can do. But by finding these Cepheid variables, we can actually get further, deeper into the Milky Way, and extend this all the way out to potentially other galaxies. And there's that rung crossover I was discussing before. Parallax can get us within this range here. All right, our best parallax measurements can do about this range. And we've got Cepheid variables that are just outside of that. So we can use our parallax measurements and our Cepheid variables, or standard candles is another phrase you'll hear them referred to as. And we can cross-reference. Look at stars that are in a crossover, try and find those, and calibrate our techniques. Now to get to the furthest, greatest distances in the universe, you're going to need the brightest objects, and that's going to be supernovas. Doesn't matter what type, type 1a, type 2b. We're going to use all types of supernovas. The brighter the object, the better it is for us using it as a distance measurement, because the peak intensity of that explosion can be called a standard candle. And what we mean by a standard candle is that you take this object and we know how luminous it has to be. As long as we know how luminous it has to be, we can call it a standard candle. Think of taking a 20-watt light bulb versus a 60-watt light bulb, right? You know how much power these light bulbs are emitting, and you can measure how bright they're going to be. So we can identify standard candles, and we think we understand physics a lot, so we can calculate how luminous a supernova of different categories should be. So we calculate how luminous a supernova is, and then go out to the universe, look at the stars, and find supernovas. With that, you can say, well, how bright is a supernova? And use our luminosity distance relationship again. That luminosity is proportional to 1 over the squared distance. I know how bright it should be. I know how luminous it should be. I've measured how bright it is. Get the distance. So, some things I want to emphasize here. This is by no means a comprehensive list of all the different measuring techniques that we use out there. That said, with all the techniques that we have discussed and plenty more that we have not discussed, there's a lot of overlap, right? One thing that happens in science, especially with distance measurements like this, is that there's a lot of uncertainty. There's a lot of uncertainty in the measurement. Basically, the technical term would be error in your measurement. Not that your measurement was a mistake or wrong. Error just refers to plus or minus how many light years are you off. Okay, that's what I mean. So we as scientists want to reduce uncertainty as much as possible. And so what we're going to do is use as many techniques as we can to confirm distances, repeat our observations. And through that, we've gone to the scales, the size of the universe.